Hello and welcome to my channel. Today I would like to talk about robust control, one of the most important concepts in modern control engineering. Robust control is widely used in applications such as autonomous vehicle, aircraft systems, robotics, medical devices, and industrial processes. So, robust control and the main concept. So, what is robust control and why do we need it? Robust control is mainly about finding a balance between performance and robustness. First, what do we mean by performance? Performance means how well the controller achieves the desired objective. For example, I may want a fast response time, fast tracking, or a controller that works effectively over a large bandwidth. Now, what is robustness? Robustness means that I can guarantee this performance even when disturbances, uncertainties, and noise are present. A system may perform very well under ideal conditions, but if a small disturbances can cause a significant degradation in performance, then the system is not robust. This situation happens very often in real-world systems. Therefore, both performance and robustness are important. However, we cannot maximize both at the same time. There's always a trade-off. If I want more robustness, I usually have to sacrifice some performance. And if I push performance to the limit, I often lose robustness. So the main question becomes how do we evaluate performance and robustness? For that, we use the sensitivity function. The most important one is the sensitivity function is the sensitivity function is equal to 1 over 1 plus gk. We also define the closed loop transfer function, and it's equal to gk over 1 plus gk, and it's equal to 1 minus s, or sensitivity function. And the controller sensitivity function is ks equal to k over 1 plus jk. These functions are the key tools used in robust control and H-infinity design. Before going further, we need to understand the concept of H-infinity norm. The H-infinity norm can be understood as the maximum gain of a system over all frequencies. When we draw a body plot, we evaluate the system gain at every frequency. The largest gain value among all frequency is called the H-infinity norm. So mathematically, as you can see, here is our formula for H-infinity norm. In simple words, we test all frequencies and look for the highest amplification. That highest value is the H-infinity norm. Now let's look at the control structure. We have a controller K and a planet G. The reference input is R and the system output is Y. The main objective of our controller is simple. I want the output Y to track the reference R. However, in reality, we also have input disturbances, output disturbances, measurement noise. Therefore, the real objective is track the reference while rejecting disturbances and noise. So to analyze this, we use sensitivity function, and the sensitivity function is s equal to 1 over 1 plus L, where our L is equal to gk. uh, and it is the open loop transfer function. The complementary sensitivity function is T is equal L over 1 plus L, which represents the closed loop behavior since T is equal 1 minus S. So both functions are directly related from an input to output point of view. Uh, the T maps the reference R to the output Y. So the main idea is that every sensitivity function maps a particular input to a particular output. The two outputs that interest us the most are control signal output, it's U, and the system output is Y. So let's understand the role of t. Ideally, I want y is equal to r, which means if our t is equal 1, this could happen. However, if t is equal 1 for all frequencies, then the output will also follow the measurement noise. To solve this problem, we work in the frequency domain. The reference signal usually changes slowly and belongs mainly to the low frequency region. So noise usually changes very quickly and belongs mainly to the high frequency region. Therefore, our objective becomes a low frequency T to be approximately near to 1 so that the output tracks the reference, and at high frequency we would like T approximately to equal to 0 so that the output rejection can measure the noise. In summary, uh, we can say the low frequency is for tracking and high frequency is for noise rejection. This is exactly the desired shape of the complementary sensitivity function T. In the plot diagram, we use a logarithm scale. Therefore, values close to 0 appear as very negative dB values rather than exactly to be 0. Now let's focus on the sensitivity function S. The sensitivity function links disturbances to the output. Since we want disturbances to have a little influence as possible on the output, we would like S to be very small at low frequencies because S equal to 1 minus T, and we previously said that T should be close to 1 at low frequency. It naturally follows that S should be close to 0 in that region. Of course, this is the ideal case. Now, let's analyze robustness through the open loop transfer function L equal gk. We study the frequency response of L g omega over all frequencies. The most important point is the critical point at -1. Why is this point important? Because if kg becomes equal to -1, then the denominator of the closed loop transfer function becomes 0. And 0 denominator means instability. That is why the point -1 is called the critical instability point. The Further, the Nyquist curve stays away from this point. The more robust the system becomes. This distance introduces two important concepts: gain margin and phase margin. The gain margin tells us how much gain variation the system can tolerate before becoming unstable. And the phase margin tells us how much phase variation the system can tolerate before becoming unstable. If both margins are large enough, the system is generally considered robust and stable. To guarantee good gain and phase margins, we introduce another measure called the modulus margin. The modulus margin is directly related to the maximum peak of the sensitivity function. A common engineering rule is that the maximum sensitivity should remain below 2. In dB, this corresponds to approximately 6 dB. If the maximum sensitivity remains below 2, we generally obtain acceptable gain and phase margins. Similarly, for the complementary sensitivity function, we usually require its maximum peak to remain below about 1.5, which corresponds to approximately 3.5 dB. Therefore, keeping the uh, these values are under 2 and 1.5. So usually provides a good balance between performance and robustness. Let's now summarize the desired behavior of all sensitivity functions, starting with the complementary sensitivity function T. At low frequencies, we want T to be close to 1 because this guarantees reference tracking. At high frequencies, we want T to be close to 0 because this helps to reject measurement noise. In addition, we would like to maximize the peak of T to remain below about equal or below the 1.5 in order to maintain stability and robustness. Now let's look at the sensitivity function S. At low frequencies, we want S to be close to 0, and so that disturbances have a minimal effect on the output. And at high frequencies, S becomes close to 1 because S is equal to 1 minus T. Therefore, the shape of S and T are opposite. When T is high, S is below low, and when T is low, S is high. In practice, perfect values of 0 and 1 are not achievable since body diagram use logarithm. So in logarithmic scales, we usually represent 0 with a very small value such as 10 power minus 3, which corresponds to approximately minus 60 dB. For sensitivity function, we would like to the curve to start near minus 60 dB and never exceeded approximately 6 dB. For the complementary sensitivity function, we would like it to start near 0 dB and remain below approximately 3.5 dB and then roll off toward minus 60 dB at high frequencies for T, I mean. To enforce these requirements, we define a template. This template specifies the desired behavior of the sensitive function. In this template, S is the Laplace variable, omega b is the bandwidth, and epsilon represents the tracking error. Uh, ms is the modulus margin. So the bandwidth separates low frequencies from high frequencies. Uh, Below the bandwidth, we focus mainly on tracking and the disturbance rejection. Above the bandwidth, we focus mainly on noise rejection and robustness. In general, increasing the bandwidth products or produce a faster response, but it can reduce robustness. The tracking error should be very small, and a common choice is epsilon equal to 10 power minus 3. At the same time, we usually require a modulus margin to remain below under 2 or equal to. Now let's discuss the controller sensitivity function Ks. The controller sensitivity function directly affects the control signal U. At low frequencies, we don't want the Ks to be zero because the controller must generate enough action to track the reference. However, we also don't want Ks to become excessively large. Why? Because the control signal is sent directly to the actuator, and every actuator has physical limitations. For example, imagine a car whose maximized speed is 200 km per hour. If we command 300 km per hour, the actuator cannot deliver that request and saturation occurs. We usually define Umax as the maximum allowable control effort, since the control signal depends on the reference and on Ks. A very large value of Ks can push the actuator into saturation. Therefore, at low frequencies, we want enough control authority, and at high frequency, we want the response to roll of towards zero. This help to reduce the influence of noise and prevents excessive actuator activity. Unlike S and T, the acceptable peak value of Ks depends on the actuator limitations and on the application itself. Finally, we have the uh, planet sensitive function Sg. Its shape is very similar to the sensitive function S. The purpose of Sg is to reject the disturbances entering the planet and affecting the system output. Therefore, its desired uh, behavior follows the same philosophy as S. So it means that the strong disturbances, rejection at low frequency, and robustness and noise rejection at high frequencies.